This will be a demonstration just to show the conservation of energy. We'll be launching a 1 mass, a half mass and a quarter mass, all with the same set amount of energy. So I'll be using a spring launcher, and each time the force will be the same and the distance will be the same. So the set amount of energy each time we launch is the same, or roughly the same. As the masses are launched, they will be sliding across the surface, so there's no rotation, there's no angular momentum or anything. They're just sliding. So here we have the 3 masses. We've got the 1 mass at 74.71 grams. And I'll just try that again. So 74.71 grams for the 1 mass. Then we go to the half mass. We have a weight of 36.77 grams. And just try that again. And we have 36.77 grams. And then the quarter mass. And we have a weight of 18.41 grams, and we'll just try that again. And we have 18.41 grams. So just seeing the masses there, so the 1 mass is 74.71. So if we divide that by 2, we get roughly 37.5, and if we divide it by 4, we get 18.67. In actuality, the half mass is a little bit under, and so is the quarter mass. So not perfect, but you know, within reason. This is the spring launcher. We just press the button and boom, so we've got a set amount of force over a set amount of distance, and this is clamped to the table in a fixed position. Launches at a set height, so when we put the 1 mass, it's just about at the centre of mass when it's launching it. When we put the half mass in, it's a little bit above, and when we put the quarter mass in, it's quite a way above the centre of mass, so obviously that might affect the results. Obviously that's clamped and fixed, I can't alter that. So just to keep things simple, just say it's a 10 mass, and when we launch it, it goes 10 meters per second. So we can roughly calculate the energy. So we've got the potential energy in the spring, and that will convert to kinetic energy. So if we use the energy formula, that would be half the mass times the velocity squared. So that would give us roughly the energy of 500. So that would be the energy that the spring is giving. Now, if the expectation was that by halving the mass, it would somehow go twice as fast, then if we look at that, we've got 5 mass going 20 meters per second, half the mass, that'd be 2.5 times the velocity squared, which would be 400. So we can see we've got 1,000 there, so we've got twice the energy. So clearly it's impossible for that to happen because we've only got 500. That's, you know, twice the energy. We'd need twice as much energy input for that to happen. So we'll go through what we should expect to see in actuality. So as before, using the simple numbers, so 10 mass going 10 meters per second would equate to 500 energy. So when we launch the half mass, it's roughly going to go square root of 2, which is 14.1. 14.1 squared is 198.81, round it up to 200. 2.5 times 200 equals 500, so we've got the same energy. So the expectation would be that it's roughly going to travel around the square root of 2, which is about 14.1. And for the quarter mass, half the mass, so 1.25. The velocity squared be 400. 1.25 times 400 is 500. So in each case, obviously it's the same energy, so the expectation would be obviously this is the 1 velocity, this is the 1.14 velocity, and this is the 2 velocity. That would be the ideal. We'll obviously see the results and see how close we get to them. So this is the 1 mass launch. I have cropped it. They were filmed from a fixed position, but obviously I've cropped it down. But we've got the physical ruler, and I'm measuring from when the mass hits the centre of the first line and the centre of the second line. And for that pass, we've got 6.2 seconds. So the same on this one. So as it hits the centre line, I'm measuring the time from there to when it meets the next centre line. Measurements might not be perfect, but like I say, with the physical ruler being there, I've tried to put the markers in, so when it's been cropped, with the physical ruler being there, you know, the distance should be the same and the frame rate the same. So that was 6.4 seconds. They're all individual launches as well. And this one, again, like I say, measurements might not be perfect, but, you know, they're thereabouts. And for that pass, we've got, what have we got? 6.5 seconds. So for the 3 passes, we got 6.2 seconds, 6.4 and 6.5. So if we add those together and divide it by 3, we average out at 6.36 seconds. So the expectation or the prediction for the half mass would be 6.3 seconds divided by 1.414, and that gives us 4.49 seconds. So we'll run the next one and see how close we get. So this is the half mass launch, again cropped, but we've got the physical ruler in. I've tried to get the markers as good as I can. So again, measuring from the centre to the centre. And that pass measures 4.4 seconds. Again, all individual runs. I did try to crop them, you know, as good as I could and get the markers as good as I could, but it's difficult. So that's launch 2, second pass. And we have a time of 4.4 seconds. And launch 3. Again, all individual launches. And that pass, I use the editing software to measure the time because it goes down to points per second, 4.3. So for the half mass, we've got 4.4, 4.4, and 4.3. Add those together, that gives us 13.1. Divide that by 3, and we get an average of 4.36 seconds. The prediction was 4.49, so well within reason. So clearly not going to arse as fast. The average for the 1 mass was 6.36, so if we half that, we get 3.18 seconds, so the quarter mass should be around there. So now we have the quarter mass, and that pass, again measuring centre to centre, was roughly 3.4 seconds. Launch 2. Also, I put the markers in that place because when you launch them, the slow-mo doesn't kick in straight away, so I picked a point, that's 3.6 seconds. I picked a point where obviously the frame rate's kicked in on all passes, so it's roughly the same distance, the same frame rate, and that pass was 3.4 seconds. So for the quarter mass, we got 3.4, 3.6 and 3.4. Add those together, we get 10.4. Divide that by 3, so the average was 3.46 seconds. We predicted 3.18 seconds, so it's like roughly, what, 0.3 of a second out. So again, not perfect, but thereabouts. So in conclusion, we can see pretty much that energy is conserved. Obviously there might be a little bit of discrepancies in my measurements, but we're pretty much there. But you know, it's interesting to note that actually in these results, even quartering the mass, I didn't quite get twice the velocity. That could be down to my measurements, but you know, to say that halving the mass will go twice the velocity, in this instance even quartering the mass didn't actually show twice the velocity. It was almost there but not quite, but pretty much shows that energy is conserved.